Here we have our guest speaker, Dr. Alessio Franchi from Liège University, who will give us a short course on neuromorphic engineering, some of its applications, and how it is related to the state-of-the-art studies of computation and brain-inspired computation and similar stuff. So thank you very much, Dr. Franchi. And here we're starting right now.
Thanks a lot, Omar and Roman, and the coordination of the neuroscience course bachelor at UNAM for inviting me. It's a really big pleasure to be back to give a course at UNAM. Unfortunately, not in presence, but maybe next year we can try to organize it more slowly and do it live. So this will be a 3-lecture series in which I will try to cover, of course, in the detail that such a short time allows, a little bit of what's neuromorphic engineering in general, what's brain-inspired computing in general, and then for each team give some details about how these things can actually be done, including which technological development they can lead to, or which technological development also motivate them. So the plan for today is that I will give more or less half an hour, I think, of general introduction to neuromorphic engineering, a little bit of its history, where it comes from, which are really the motivating ideas of these fields of engineering, and then go toward CMOS circuit design. So really how to put together transistors, in particular in particular MOSFET, so NFET and PFET, in order to realize brain-inspired dynamics and neuromorphic dynamics into state-of-the-art chips. First of all, please stop me whenever you want. I think it's much more. Most of the things probably will be very new to you. So in case there is something I did not explain clearly, something you want to ask more about, just raise the hand. Maybe Omar, you can kind of share the lecture and check if people raise their hands, and I will try to answer. So neuromorphic engineering, as the name says, it's a form of neuro-inspired technology, and one of the main objectives of this neuro-inspiration is to make artificial intelligence a much more sustainable technology. Because as you know, or as you might know, at the moment, training networks like ChatGPT and similar is already draining more energy from the planet than all the international flight and all the flight put together. So there is an urgent need to make artificial intelligence more sustainable, less energy greedy, and an idea to achieve this is to use neuro-inspiration. Why? Well, because we know that our brain consumes essentially the equivalent of 20 watts, when even the most basic GPU in your computer consumes at least a few hundreds. So one of the main reasons for which standard artificial intelligence is not energy efficient is that it's based on the von Neumann architecture, that is the standard architecture of digital systems. So in a digital architecture, what you have is, well, first of all, a clock that coordinates all the elements to update operation, read memory, write memory in a very synchronous way. So all the elements of a digital system are perfectly synchronized. And what you have is a memory. So memory elements are basically shift registers that can be more or less large, that can be more or less close to where the computation is done. They can be more or less fast, more or less slow, depending on the technology. And together with memory, you also have not in the same structure, but separated from memory, you have the CPU, the GPU, and all other form of logic units that really process information and do all the things we can do with digital machines. The problem of not of essentially having memory separated from the central processing unit is that moving information, moving bits of data between the different parts of a digital systems is extremely energy greedy. That's why also, and the problem is that if you try to put the memory together with the CPU, well, then you have, for instance, what's called the level 1 cache, which is which is already really in the same die, on the same piece of silicon where the CPU is. In such a small place, it's very difficult to put enough memory to do everything what you want to do with a computer, store videos, and so on and so forth. And that's why you cannot really put memory super close to the CPU, but you need the L1 cache. That's the only one that's really on the same piece of silicon as the CPU. Then you have L2 cache, which are close by but already not on the same silicon piece. Maybe level 3 cache, and then you have RAM, and then you have the hard drive essentially. And then on top of it, you also have the cloud. And of course, moving the data back and forth the cloud is the less efficient way of doing things. But unfortunately, it's becoming more and more common that we delegate part of the computations, say, to Overleaf for writing tech, or to Google for training GPUs to solve machine learning tasks. So the first goal of neuromorphic engineering is to go beyond the Neumann architecture. And that's, of course, something that is motivated by something that will arrive in a moment, but it's also a very difficult task because 99.9% of our technology is based on this architecture. So what's needed is really a shift of approach, a radically new approach that can allow us to go beyond this architecture. Despite the fact that it's very versatile and mature, I think it would be a lie if we would not admit that programming in C++ or Python or assembler, it's something that's been done for what, maybe 50 years, maybe slightly less, but it's something in which we have worked a lot to make it fast, to make it scalable, and so on and so forth. And indeed, there are many successful industrial applications, probably all controllers, all interface, all technology we have at the moment, from our car to our laptop to our cell phones and so on and so forth, really use this architecture. The problem is, as I was saying, that this architecture is extremely energy efficient. In more, I would say, abstract or not really, well, I think you can approach this problem also from a philosophical perspective, that the intelligence of any machines that's implemented in a digital architecture is intrinsically limited by its algorithmic nature. Even if you take ChatGPT, that seems to be able to respond to our question in a kind of creative manner, there is surely nothing new that can come out even from huge machines or huge algorithms like ChatGPT, because essentially anything they can do is put together ideas that they that they stole, I would say, from the internet, and maybe they can recombine in some way, but these will be the way in which they recombine them and the type of seemingly new objects and songs, figures that they can create is essentially limited by a combinatorial recombination of all the information that they take from the internet. And although this number of combinations can be huge, for sure there will never be something really new coming out from a digital machine. And finally, that the principles on which they are based are very different from the principles and mechanisms over which biological intelligence is built on. And of course, as neuroscience students, you know that understanding biological intelligence is not a piece of cake. It's something that we have been working on, there has been research on for many, many years already, but still our understanding of the brain is still in, I would say, in its infancy. However, some mechanisms, some possible universal mechanisms already start to have been isolated, including the work of Roman. Part of my works, although my work is much more at the cellular level, at least my really neuroscience work in the last 10 years. But still, being it at the population level or at the cellular level, some important mechanisms are being discovered. And so probably now it's a good time to try to go beyond digital intelligence. So just to give you an example of the huge difference in scale, in efficiency between digital and biological intelligence, take, for instance, the example of a bee. I don't know if you can see it here. It's on this flyer. On this flower, you have a small bee. So the brain of a bee counts more or less 1 million neurons and 1 billion synapses. It is, I mean, approximately it consumes 10 microwatts. And despite this very small size, particularly if you compare it to large artificial neural network like ChatGPT, despite this tiny brain, a bee can fly acrobatically in an extremely skilled fashion. It can recognize pattern. For instance, to recognize their peers or flowers or objects that they need that they see and need to recognize when they fly. They can navigate, and in particular, they can build a mental map of the environment they live in, and they can remember where they spot a good site for extracting the pollen from flowers, for instance, or a good site to build the next nest in which they will live when the one they live in becomes too small or whatever. They can forage, so together they can explore the environment, detect where there is more food, more resources, communicate between each other, the good places, and go to them to forage. And they have various ways of communicating between themselves. So the best known way probably is what's called the waggle dance. That's this body movement, this walk that they do to indicate through a geometry that I won't explain here, location, for instance, of a good foraging site. And now if you compare this to an already quite old CPU like the AMD Ryzen, well, it has 5 billion transistors. It is probably larger in area than the brain of a bee. And it consumes what? So we are going from 10 microwatts to 180 watts. So we are talking about 7 orders of magnitudes of difference in the consumed energy. And moreover, what you can do with an AMD Ryzen is not at all in line with what a bee can do, in the sense that a bee is way more intelligent than an AMD Ryzen. And okay, if you go to more modern CPUs or even worse GPUs, you will see that these numbers are just keep on increasing. Just to give you an idea, a 1 millimeter of cortex, but this probably you already know, contains more or less 1,000, more or less 100,000 neurons. But although there is 100,000 neurons, you have 1 billion synapses, in the sense that the neural network that implements biological intelligence are much more densely connected than standard digital artificial intelligence systems. And again, although our brain for sure consumes more than the brain of a bee, we are still talking about 1 milliwatt for each cube millimeter of cortex. So the goal of neuromorphic engineering is really, okay, I repeat myself, going beyond digital architecture, designing and understanding brain-inspired computational algorithms and realize them into efficient electronic design. Why electronics? Well, because electronic is, although mostly used for digital machines, it's a very well-developed technology. And so it is natural to remain inside that technological framework, although we want to change completely the way in which we use and exploit that digital substrate, that electronic substrate. The goal, again, is to drastically reduce the energy footprint of computing machine. And something, again, slightly more philosophical is that if we go analog, then we are not restricted by algorithms. And so maybe that's also a way to increase adaptability, the resilience, in a sense, the creativity of artificial intelligent machine. And this with the goal also to expand the fields of application of artificial intelligence, because essentially you cannot put ChatGPT, let's say, in a prosthesis. Whereas if you use more brain-inspired method, maybe we will be able to have intelligent prosthetics, intelligent exoskeleton design, artificial sensing, so sensors like camera or touch sensors that already possess at the sensor edge some form of intelligence. Again, with the idea of not having to transmit data back and forth, the sensor and a GPU, and then maybe sending back to the sensor to adapt its functioning, but to have intelligence really at the sensor front end, at the sensor edge. Soft robotics that also needs new ways in which we can control soft robots, and brain-machine interfaces, just to mention a few. Any question? Okay, so the principles that neuromorphic engineering exploits to achieve this goal is, first of all, the fact of using event-based information. So event-based information processing and computing is really the engineering way of defining processing and computing and more in general intelligent systems that essentially use spikes or mostly spikes to transmit information between the different components of the system. So each time you will see the word event-based in this presentation, think about spikes and think about the fact that in our brain and in our central nervous systems in general, any form of information processing and computation is based on spike. In-memory computing, so the idea that, again, like in the brain, you don't have a part of the brain that contain your memories, a part of the brain that work like a CPU that needs to access this memory, retrieve information, processes them, maybe mix them with sensors, with sensor information, and then transform it into a motor output. In our brain, each part of the brain is both a place where memory is stored, not only bibliographical memory, of course, but also memory related, for instance, to receptive fields, to computational primitives that need to do some computation. And so any form of knowledge, any form of memory that we have in the brain is strictly mixed with computation. And so the prefrontal cortex both store experience and computational primitive to make the decision it has to make. At the same time, it receives information flow from other cortices and process information in memory. Another important aspect is the use of emergent computation. So the fact that we can use nonlinear neural networks and nonlinear dynamical systems to design way of processing information in a way that uses the emergent of patterns, of states, of oscillation, of many things that you can observe in the linear dynamical system and exploit this emergency for rich and adaptive information processing. Embodied intelligence is another fundamental principle of neuromorphic engineering. So the fact that, again, because we are not separating processing units and memory, and we don't want to separate sensory processing from the sensor, essentially we can rethink the way in which we design sensors, in which we design actuators for robotics, for prosthetics, and so on, in a way that really exploits the mechanics, the embodiment of the sensor, in a way that's from the beginning tightly coupled to the sensor, to the neuromorphic processing layers. And also something that's inspired by biology is to start to focus more on resilience and robustness instead of pure brute performance. So in artificial neural network, usually the only criterion that's respected to validate a new deep neural network you want to publish is that you manage to move from 99% accuracy to 99.5% accuracy. Whereas we already know that biological systems are much more imperfect. We never have perfect performance in any of the tasks we do unless we become a pianist and train for playing the piano for 20 years. And then after 20 years of having played the piano for 8 hours a day, then maybe we reach some form of perfection in doing some tasks. But in general, if you take the standard intelligence you use to move from one room to the other, to cook, to answer the phone, to ride your bike, to walk, to engage in conversation, to thinking, and so on and so forth, in all of these much more common ways of being intelligent, we are far from perfection. We are far from the best performance we could achieve. But at the same time, we are very robust to variability. We are very robust to changes in the environment. We are very robust to perturbation. In a word, we are resilient. Similar, in line with this point, the idea is also to start to shift the attention from speed, from doing computation extremely fast, to energy efficiency and adaptability of these machines. So I would like now to tell you about probably I would say for the moment, I don't know if it's the only one, but for sure is the most notorious one, the most commercially successful one, the one that's really entering our technology as an outcome of neuromorphic engineering, which are event-based cameras. So I won't detail in these 3 lectures the electronic aspect of event-based pixels because it will take too much time. It's already a kind of complicated, advanced analog CMOS circuit design. But I will give you kind of the functioning aspect of event-based camera, and then maybe if I have time, I can go back to the pixel structure from more or less high-level perspective. So I think I don't need to put such a slide in front of such an audience, but just to recall to recall ourselves that what comes out from the retina is not at all an image of what we have in front of the visual field. Okay, we have no frames, we have no images coming out from the retina. This perception we have at this moment is reconstructed in our consciousness somewhere, but for sure there is not a single part of the brain in which you can really find a snapshot of what the person is looking at. What you can find coming out from the retina are trains of spikes or train of events. So each time you have a spike, you can say spike, 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 or when you hear a raster plot, you can click each spike, but I think we all agree that a spike is a temporal event. It's something that it's either there or not. And when it's there, it comes with a precise time stamp. And this train of spikes, depending on which ganglion cell you're recording from, can encode for temporal contrast of what's been seen. So maybe they're encoding for rapid changes in the luminosity at the receptive field of the ganglion cell. They can encode for spatial contrast. So maybe only the fact that there is some texture or some variation in luminosity in the receptive field of the ganglion cell we're recording from. Or maybe movement, as we know already that there are many ganglion cells that only fires when, for instance, there is a movement from left to right inside the receptive field. So essentially what we have at the output of the retina is many trains of events that contain essentially already semantic information about the external world. For sure, what we don't have are frames, again. And so the idea underlying event-based vision or event-based camera is to be inspired by the function of the retina, and so designing a camera that instead of having frames at its output, has events at its output. Let me close this. Okay. And so this is exactly what you have at the output of an event-based camera. And just to give you an idea of what an event look like, if you transmit these events through a USB, through a serial connection to your computer, each event is characterized by a timestamp. So the time in what these are, so milli, macro, nanosecond. So the time with nanosecond resolution of when the event was emitted. Then you have the position of the pixel that emitted this event, and each event has a polarity 0 or 1, where polarity 0 means that brightness was decreasing at the pixel, and so the pixel generated an event because it's saying light is decreasing, light is decreasing, light is decreasing. And a 1 if the brightness was increasing at the receptive field of this pixel. So we can already make an important comment that is an event-based camera will not emit events. There will be nothing that's transmitted to the serial connection, and so there is zero energy consumption if nothing is happening in front of the camera. Okay, so if you have a camera, if you use an event-based camera, for instance, for recording for security issues, for security applications, so you want to use it for surveillance. If there is nothing that passes in front of the camera, then essentially the camera will go to an idle mode. We go in a sleep mode in which it will generate zero event, and so there is zero misuse of energy from this type of camera. Of course, the same is not true at all for standard cameras. And the important thing is that this form of already embodied intelligence, so this fact of sending information only what's needed, it's really happening at the pixel level. There is no algorithm, there is no digital machines that needs to detect if something is happening and maybe call the pixels and ask them to send something, which would be, again, very energy inefficient. The fact that an event-based camera doesn't send information if it's not needed is given by the pixel design. And in particular, the fact that each pixel is an analog filter that integrates information in analog, so very energy efficient fashion until a threshold is reached. And when this threshold is reached, an event is generated. Any question? Okay. So this is, I don't know if you see, do you see this part of the slide smoothly? The event-based camera output?
Yes, it's smooth.
Okay, so in the case I will send you the slides of this presentation, so you will have everything to rewatch it if you want and see it better. So this is a comparison of a standard camera and an event-based camera watching the same, looking at the same thing. Most of the event-based camera has both a standard RGB or black and white CMOS sensor, and side by side you have a standard digital frame-based sensor and an event-based sensor in order to be able to do such kind of experiment, particularly for research development. And so as you can see, the scene is quite dark, and as a consequence, the standard camera already starts to lose kind of details and like correctly see the image. For instance, here you see that you don't really see the borders of the books, whereas the event-based camera is clearly able to detect these three borders together. Same for the border between this cup and this other cup, which this border is basically invisible in the standard camera and becomes super clear in the event-based camera. The leg of the table that here are visible, whereas here are completely invisible, and so on and so forth. So an event-based camera has various advantages. First of all, there are no frames, so the temporal resolution is equivalent to a few thousands of frames per second, even more if you want to go to really high-speed application. And secondly, for the way again in which the pixel is designed, without using any filter, without using any amplification, any high expenditure amplification process, is able to have a huge dynamic range as compared to a standard camera. And so this is an application of this idea to high-speed vision, in particular high-speed vision during night.
Propose a method to continuously reconstruct image intensity.
Oh, sorry. I will. So what we see here is to avoid using the bar. So what you will see in the first video is a comparison between an event-based camera and a frame reconstruction, a continuous time frame reconstruction. So frame images that you can zoom in time as much as you want. That essentially mixes a standard camera with an event-based camera. And this is for a pedestrian that's running in front of the light of a car. So as you can see, first of all, because the standard camera uses frames, whereas the event-based camera works in continuous time, works in a frameless fashion, the pedestrian is already visible in the frames reconstructed from the event-based camera, whereas it's not here. So if you imagine using this technology for self-driving car, you will also get not only something that's more efficient, but also something that's safer because it's faster. And moreover, because of the high temporal resolution of the event-based camera, essentially you have close to zero motion blur from the data reconstructed from the event-based camera. Then you can watch. Okay, this is the structure of the filter that's used for computing these continuous time frameless videos. But I think you can watch these on your own, and then if you have a question, you can ask me. What I would like to do is to show this part here. And so in particular, quite so slow. Sorry. Okay, so in the part we look at now, please observe the dynamic range of a camera. So the fact that of the event-based camera, so the fact that in an event-based camera, it's totally robust to having scene with high brightness and part of the scene with high brightness and part of the scene with low brightness. So with a standard camera, it's basically impossible to see at the same time. This is terrible. Sorry. Then I will move on to not use too much time here.
Many events.
But with the standard camera, as you can see, okay. So as you can see, for the standard camera, you have the interior of the room that's totally underexposed, and the exterior, which is completely overexposed. And so essentially, either you see completely black inside or completely white outside. You cannot see both part of the scene simultaneously. Whereas for us, it's very easy to see both inside and outside a dark room simultaneously. And this is exactly what happens with the event-based camera. Then I will let you look at the video on your own. But as you can see, the exterior is completely visible and the interior as well. You can even see like the border here of this part of the window. Then yes, so here you have another example
Instructs clear details
with event-based camera. So you can see the one that's reconstructed from the event-based camera. You can do a slow motion with extremely high temporal precision, and you will look at this full video on your own. And so the main advantages of event-based camera that are making this technology present also in some cell phones, in some self-driving technologies, is the fact that it's extremely fast. It has virtually no motion blur. It is on demand, so it transmits information and asks for this information to be processed only when it's needed, and it has an extremely high dynamic range. The main problem with event-based camera that also motivates part of the research I do in my group is that there are basically no efficient neuromorphic algorithms or layers or event-based processing systems that you can plug at the output of an event-based camera for processing these the perceived scene in an event-based fashion end-to-end. And so usually what people do at the moment is that they window the event into time frames, but these time frames now uses events instead of RGB and process these kind of windowed event-based information with standard deep neural network, for instance. And so in a sense, that's kind of a pity because you have a camera that's super efficient, that's already very intelligent, and then you're plugging its output into the most standard machine learning algorithm, thus essentially losing the advantages of event-based vision at the first synapse after the sensor layer. So I think this ends the introduction to neuromorphic engineering. I will go back to the application part at the end of the lecture. And now what I would like to do is let me stop sharing this window and I will share another window. Do you have questions? Okay, so give me 1 second to open this presentation. And so where is notes? Okay, so you see my notes already?
Yes.
Yeah. Okay. So why didn't open? It's here. No. I have imported it inside. Why isn't it opening? Okay. Okay. So now the lecture will become slightly more formal and detailed in its flavor. And in particular, I would like you to see a few neuromorphic circuits really at the transistor level. So I hope you understood the motivation behind neuromorphic engineering. Now I want you to know a little bit about the way in which these things are done in the real life, and then we go back to application once this basic knowledge will be acquired. So neuromorphic circuits, I mean, people are starting to go beyond CMOS and MOSFET technology, which is, again, the standard technology used for CPUs and GPU. Maybe for neuromorphic systems, which are mostly developed in university, we do not use the latest CMOS technology because maybe now the last CPU from Apple is using a 10 nanometer process, whereas, for instance, in the chip that we produced in my group, we are using 180 nanometer technology, so a technology that was current for CPUs and GPUs. Well, GPUs not 15 years ago, for CPUs maybe 15 years ago. But besides using a slightly older technology because it's much less expensive, so essentially producing these chips is extremely expensive. And so if you want to do them in the latest technology, maybe you will need to spend 100,000 euros for a single for producing a single run of chips, and maybe getting around 30 of these chips. Whereas if you do it in 180 technology, maybe now each run of chips cost around 3,000 euros. So it's never cheap, but it's much cheaper if you do it in old technology. But the idea is to develop circuit design that we know are compatible with newest technology in case there will be some commercial development, in case there will be some valorization or something that will need to scale the production up to a larger scale. In which case, of course, it makes sense to invest much more into chip production. So the idea behind MOSFET is to use semiconductors, and in particular, essentially a FET is a pair of NP junctions to create something that can be used as a switch, essentially, something that allows you to generate nonlinear circuit behavior. The most basic, most exploited one is to interconnect two or more transistors in some positive feedback interconnection to realize digital bits. So if what's a memory element realized in MOSFET is essentially transistors coupled in a positive feedback in such a way that you get something that's either fully open or fully closed, so something that can represent zeros and ones. And usually there are two types of semiconductors that are used in MOSFET design. Semiconductors that are doped with donors, so atoms that tend to donate electrons in such a way that, although it's not a metal, although it doesn't conduct electricity as well as a metal material, you still have free charges that can travel along these semiconductor. And the other type is the P substrate that is doped with acceptors. So atoms that tend to accept, that have a lack of electrons in such a way that now what's traveling is the lack of an electron. And so if you remember that an electron is a negative charge, the charge that travels in N-doped material are negative electrical charges, whereas what travels in P substrate are positive electrical charges. And when you put them together, what you create is an NP junction. And we look at the moment what does this mean and why it's important. And just to introduce the notation, there are different ways to represent differentially MOSFET that are based that have P wells inside, so P semiconductors inside a well of N semiconductor, or vice versa, transistor that uses N, N-doped, N-type of semiconductors inside a substrate of P semiconductor. Usually the substrate is silicium or other type of closely related material. And then you have metal and everything that you need to really transmit information along the rest of the circuit. And so as you can see from the symbol, each transistor has three terminals, what's called the drain, the source, and the gate. So each one, let me start to draw. That was the idea. So each one of these three ends of a MOSFET, these three ones, are electrical terminals that you can use to interconnect the transistor with other transistor or with other electrical or electronic elements. So what you have here are really electrical cables. So what comes out from a transistor is really a metal, something that can conduct electron very rapidly. The structure, the semiconductor structure I just described, remains inside this part. Just to be sure, did you already see somewhere this notion? If yes, I can go faster, or this is the first time you see these things. Hello?
They
For
say
me,
it's the
it's
first
the
time.
first time.
Okay, perfect. So of course, I mean, I'm just giving you the the most basic information about electronics and MOSFET in particular. But I think it will be enough to understand how to use them for neuromorphic circuit design. And then if you want, I can send a very nice book, a neuromorphic engineering book, where you can find all of this idea, but developed in a much deeper fashion. Okay, so this is what a transistor look like. So these are the symbols that we use to design and draw circuits that contains transistors. But actually, if you can zoom, if you can take a micrograph, a photograph of a chip, a transistor look more like something like this, where in particular you have the two, you can see really the two semiconductor the substrate, and then this, which is just a metal, which is the gate of the transistor. And so what my students did when he produced the first chip, and I will show you a photo of what he did in a moment, probably today, or maybe he will present the 28th, so he will be able to show you more about these kind of things. But essentially, when you design a chip, what you do is literally draw where you want your semiconductor pieces, and then this goes to the foundry, and they use mask and lithography and other techniques to literally build to realize your drawing. And the same is true for digital chip design. And in particular, because you are really drawing each transistor one by one, you can also change the geometry and the shape of each transistor. So in particular, decide how long is the channel of the transistor. So the channel, I will go back to this, but just to introduce the word. So the channel is this part here between the two doped end of the transistor. This is where it's called the channel, because it's really where the charge will travel when you activate your transistor. So the length of the channel is called L, and its width is called W. And if you remember the law of resistors, because I mean it's a nonlinear resistor, it's not like a standard resistor that satisfies Ohm's law, that is V is equal. So delta V is equal to conductance times, so the current flowing through a resistor according to Ohm's law, if the resistor is linear, is simply the conductance times the difference, the potential difference at the two terminal of a resistor. A transistor is not at all a resistor, it's highly nonlinear, and that's what interests us because it allows us to realize nonlinear operations in a continuous time fashion. But in general, but eventually, I mean, if you freeze the behavior of a transistor, what you will see are literally charges that tries to travel from this from this part of the semiconductor to this part of the semiconductor, and so this movement of charge makes each transistor essentially a conductor, but a very nonlinear electrical charge conductor. But still being a conductor, this means that the wider is the channel, the more space the charges will have to travel, and so the higher will be the conductance of this conductor, and vice versa. If you make the channel narrower, then the conductance will decrease or the resistance will increase. So this is also equal to delta V over the resistance of the conductor. And vice versa, if you make this longer, then charges will have to travel more. And so again, if you make it longer, the conductance will decrease, whereas if you make it shorter, the conductance will increase. And so deciding the width and the length of a transistor will affect its behavior, and we'll see an example of this, of the effect of changing the geometry of the transistor on its electrical characteristic in a moment. So for the FET, which are the one that carries electrons, the top terminal is called the drain. So as you can see, a transistor is a perfectly symmetric device. So there is really, at the moment, if you look at a transistor without applying any voltage at its terminal, you have a device in which you can flip it left and right without changing at all its geometry, and so without changing its behavior. However, because in electrical circuits we always have a battery, so we always have a potential which will be called VDD, which in the technology I use is 3.3 volt. So this is really the source of energy you need to provide to a MOSFET circuit, being it digital or analog, to turn it on. And so usually when you draw circuits, you put VDD on top, then maybe you will have other part of the circuit that we don't draw here, and then you have maybe a cable that arrive at this transistor, and then maybe you have other parts of the circuit here and other parts of the circuit here, and then at the bottom you have the ground, so the zero potential, okay? And so because of this vertical arrangement of circuits, and because once you apply voltages, there is a difference between the two terminals of the transistor, then we can distinguish these two terminals and call them drain and source, whereas this third terminal will be called a gate. So why drain? Well, because if you remember that electrons has negative charge, if you have a current that's flowing from drain to source, actually what you have are electrons that are flowing in the opposite side. Why? Well, because if you have negative charges that goes from down from the bottom to the upper part of the transistor, these will correspond to a net current that's flowing in the other direction. And because usually VD is larger than VS, what you want is to have a current that flows in this direction. And so because the source, so the drain is the part that is draining literally electrons from the semiconductor. That's why we call it drain. And the source is the one that's emitting the electron, and that's why it's called the source. So if you go to FET, you have the opposite situation, because now what's traveling are holes, are lack of electrons, and so the flow of the current is in the same direction as the flow of charges. So B plus. And so now the source is at the top part, which will be a higher voltage. The drain is at the bottom terminal. And then exactly like for FET, you have the gate. Okay, so what's the working principle of a MOSFET? So the main aspect, the most important, well, not the most important, but surely a fundamental object is the NP junctions, so or PN junction. So the physical region that lies close to where a p-doped semiconductor touch an n-doped semiconductor. Why is this region so important? So first of all, charges can travel inside each semiconductor, but they cannot leave the semiconductor. So there is really no net charge exchange between these two. But because the p-doped semiconductor has free positive charges, and the n-doped semiconductor has free negative charges, this means that part of the positive charges of the semiconductor, this should be different. Yes, this should be plus, and this should be minus. So essentially what you have is that negative and positive charges attract each other. And so because you're putting together a material that has free positive charges and another that has free negative charges, well, in the two material, there will be an accumulation of negative and positive charges respectively. at the two sides at the two sides of the NP junction, which is really the part here in the middle. And so because of this, because now you have an imbalance of charge, what you're creating is an electric field. Okay, so now because you have a higher potential where you have positive charge and a lower potential where you have negative charge, now what you have is an electric field that's creating a force that tries to move the charge in the opposite direction at the charge at the electrostatic attraction between the two forces. And in particular, this electric field or electric field will create essentially a barrier for the electron for the charge to be able to move from one point from a region to the other. And so this electric field, you can really imagine it as a hill, because now you have an electric, so you have an NP junction here. So here, this part here is really where you have the NP junction. So all of this is an NP junction, but for a reason will be clear in a second. So everything I'm highlighting here is an NP junction, but for a reason I will say in a second, the only part that will interest us of these NP junctions are the ones that are here close to the gate. And so this 2NP junction creates essentially a hill, a barrier that impedes that there will be charge that moves from this semiconductor to this semiconductor. What's the principle? Why these PN junctions are so important? Well, because if you now put a voltage here at the gate, and let's do the reasoning with a FET. So imagine you, with an MFET, so where the semiconductor regions have free negative charges. So if you start to increase the potential here and make it positive, there will be, so the electrons that are here are being attracted toward the gate that will be at a higher potential. And so because we are talking about quantum materials, so it's true that there cannot really be physical transport. So you cannot really penetrate the other material, but because we are at the nanometer scale, so we are close to the atomic scale, you can have some of the charges that are able, so some of the electrons here that are able to move to the other part of the semiconductor by quantum effect, by a quantum physics effect, which is called the tunnel effect. So the fact that because electrons and atoms are represented as as density waves in the quantum mechanics approach, and because you can have probabilistic effect in which some electron with a certain chance, so that the wave function of some electron can have a non-zero probability of having some part of it on the other side, while you constantly have electron that jumps from one side to the other. And but usually, so if the voltage gate is not high, then there is nothing that really pushed the electron toward this tunnel effect region. And so it's like, although there is some net flow of current, some electron that constantly jump from one semiconductor region to the other semiconductor region in both directions, the probability is very, very low, because essentially the barrier that the electron has to cross is very high. But now if you increase the voltage, and let me put this on the other side, if you increase the voltage of the gate, now this positive potential here starts to pull the electron toward the tunnel effect region. And so now, due to tunnel effect, because the energy has decreased, now you have many more electrons that can jump from one side to the other. And in particular, you start to have non-zero electron density also in the channel region. And so if the drain and the source have exactly the same potential, then the number on average, the number of electrons that you have that jump from drain to source is exactly the same number of electrons that jump from source to drain. So you have zero net current, although you have charge that travels between the two semiconductor region. But now, if you increase the gate voltage, and for instance, you also make the drain voltage higher than the source voltage, well, now what you have is that more electron, so there will be a higher probability that electron jumps from source to drain because you have positive potential here and negative charges that are traveling. Then the probability that the neuron can jump from drain to source. And so now you really have a net flow of electron from source to drain, and so a positive current that travels from drain to source. Any questions? Please tell me if I'm going too fast in this part. Okay, so what's the MOSFET characteristic? Well, you can start to look at how the current, so the main output of the transistor, at least when we try to understand its behavior, it's the current that flows from drain to source as a function of the various voltages that you can apply to the transistor. And so what you can characterize is essentially IDS as a function of the various voltages. For instance, fixing, in particular, the two voltages that you can vary are the gate to source voltage and the drain to source voltage. And so what this figure represents is how this current varies when you fix VDS to some positive value, for instance, something around 0.2 volt. And you gradually increase the potential difference between gate and source. And so this is the result of measurement, or maybe these are simulations in some very physically grounded simulation of a transistor, but experiments look exactly the same. So what you see is the following. So first of all, observe that the current is in logarithmic scale, whereas the voltage is in linear scale. And so you can see that in this part here, you have something that looks a lot like a straight line, but in a log scale. So if you see something that's a straight line in log scale, what's the actual relationship between from voltage to current?
It's a log exponent.
It's an exponential. Okay, so if you see that log of I is some linear function of V, well, this means that I, if you apply log to both sides, you have that I is an exponential function of V. So, and as you can see, so more or less this linear region, which is called the subthreshold region, and I highlight it because this is the region where you have very tiny current, so very low power consumption, and this is where we will do all the design, whereas the above threshold is the region that's used for digital design. So in the subthreshold region, you see that you go from 10 to the minus 12 ampere, so minus 12 I think is femto. You're going from a few femto ampere, which, by the way, so when you are in the femtoampere regime, it means that you have a few, literally less than 10 electrons per second that are traveling in a net fashion from the source to the drain. So you're really at the very small number limit. You're really using each charge on itself to something around nanoampere or hundreds of nanoampere. And so this is true only when VGS is more or less, in the technology we use, is between 0 and 0.8 volt. So as long as your gate current remains in this region, you have that the current varies as a exponential function of the gate to source voltage. So why do we like it? Why do we like so much the subthreshold region? Well, again, one reason is that it corresponds to a very low power consumption regime. The other reason is that if you remember, for instance, a conductance-based model, then you will remember that, for instance, the activation functions for, say, the sodium current activation is a Boltzmann function that is a sigmoid that goes something like e to the v minus half activation potential, maybe by some constant, divided 1 plus e to the kappa v minus v1/2. And so this gives you how the conductance of the sodium current change as a function of the potential. And so maybe here you have minus 40 millivolt, and the conductance that goes from very small to very high in a sigmoidal fashion when V changes from below to above this half activation potential. And so this is to say that if we have an object through which we can realize in physics exponential function, then you already have something quite rich through which designing brain-inspired, neuro-inspired type of circuits. In other words, the exponential function is a very rich function. It has a region of small slope, like all the part, the tail of the exponential essentially, and then part in which the slope becomes very, very large, and the slope is 1 at the origin for the exponential. And so a function like this already gives us a lot to work with when we want to design systems through by interconnecting transistors. And this is what we are going to do today. In particular, if you work out the physics, so quick comment, so the exponential function that you see here is a consequence of statistical physics. And in particular, the Boltzmann function. Of which I don't remember almost anything because I think I saw 20 years ago. But what I remember is that when you look at how density of object that moves according to statistical physics, like here, that involves essentially, I think this is a Boltzmann function, if I remember correctly. Yes, maybe Roman or other can comment, but I think the Boltzmann function is exactly this sigmoid. And so essentially you already have the right function to implement something that looks like neural dynamics. And if you work out the physics a little bit, you realize that for an FET, so again, FET, remember the current, the electron moves from source to drain. So the charge that moves are negative, but you always express the drain to source current for both FET and PFET. So the expression you get to is a parameter that is IN0, that is essentially the leak current of the transistor. So the current that you have also when you keep all potential to 0, because you are dealing with stochastic quantum object, you still have a little bit of current that can flow from one terminal to the other. And this current essentially fits the scale of the current through the transistor. And then you have, so I'm using G to indicate GS. No, sorry, this is really VG, so the potential of the gate with respect to ground. So VG, VS, VD are measured with respect to ground, to the zero potential of the circuit. And so you have an increasing exponential because remember, if you increase the gate voltage, then electrons tend to be closer to the tunneling region, and so the current increase. And then you have, inside the parentheses, you have an exponential that decrease with the source voltage, and this is also normal because the current is always flowing from drain to source. So if you increase the source potential, electron will want to stay more at the source, and so the current to the transistor decreases. Minus exponential of minus the drain voltage, and because you have minus here and minus here, this tells you that if you increase the drain potential, then the current through the transistor is increasing. So this is true when the charge that travels are electrons. But if now you have holes that travels, essentially the sign of this potential is reversed. And now instead of, so what enters the exponential is not the voltage with respect to ground, but the voltage with respect to the battery, with respect to VDD. And this is why a detail that, so yeah, you see it here. So here you have the gate, the source, and the drain voltage. Another voltage that I did not mention is the bulk voltage, VB, that is the potential at which you keep this part of the, so this is the bulk, is the physical region between that in which you emerge the semiconductors. And so now usually for so for FET, VB, so we draw it here. So VB is usually at 0 for FET. So you keep it at ground. Whereas VB is usually equal to VDD, so to the largest, to the maximum potential you can have in this circuit for PFET. And so in the exponential, first of all, you have the sign is reversed, and moreover, you are not comparing to ground, you're comparing to VDD. But if you stop and think about this, all this expression makes sense. Why? Because again, if you now decrease the gate potential, then because what's traveling are, so sorry, if you increase it, because what's traveling are positive charge, then you are pushing the holes, this positive electrical charge, away from the tunnel region, and this similarly for the other potentials. Okay, any questions?
No questions, Doctor.
Okay, so I will now give you a sort of list or menu of neuromorphic building blocks, starting from one MOSFET circuit. So really looking at each transistor for what it is in itself, that is a circuit, although with a single element, but still with three terminals. So I will always put the expression for the current through the transistor here on top. I will do the development only for FET, but an exercise that you can work on, and I will correct it if you're interested, or maybe I will discuss with Omar if we should add this exercise as mandatory for the course. And an exercise is to, so exercise, redo all derivations for FET. Okay. So first of all, the first things I would like to do is to explore different regimes of the transistor behavior. And in particular, if you put the source voltage at common factor of these parentheses, what you get is this expression. So you have an exponential here that it's kappa Vg minus Vs. Sorry, I forgot to mention that kappa is the form factor of the transistor, and it depends on many properties of the physical realization. But you can assume that kappa is around 0.8. And another thing to mention is the thermal voltage that corresponds to the tiny flow of charges that you have at a p-n junction. No, sorry, it's the voltage difference due to this electric field. And so in particular, you have a voltage difference between the p dot part and the n dot part. And so this voltage is ut, and it's the voltage with respect to which you normalize voltages at the exponent of the exponentials. So if you factor this exponential here, then what you get is this difference, 1 minus exponential of minus Vd minus Vs over Ut. And so if this condition, which is called the saturation condition, is verified, this condition here, so you see that what you get here is exponent of -4, or exponents of a number that's larger than 4. And if you compute exponent of 4 on your cell phone, you will realize that this is already a very, very small number, which means that you can neglect this term here. And approximate the transistor behavior as a single exponential that now depends on kappa Vg minus Vs. We will use this in a moment to build more complicated circuits. The other regime, so this is correspond to the case in which Vd minus Vs is large or large enough. Now we go to Vd minus Vs small and potentially negative. So this is Vd minus Vs large. And in this regime, essentially the transistor works like a standard, well, almost standard resistor. So an object that can transport charge as a function of the potential difference at the terminal of the resistor. And so in order to derive the expression for the transistor when this number is small, what you can do is to factor both exponential in the following way. So you factor minus Vd plus Vs divided by Ut at this in this expression, this expression here. And so if you do the computation, you realize that what you get is this term here. And so you see you have exponential of Vd minus Vs, and here you have minus exponential of minus Vd minus Vs. So if you use Taylor expansion of the exponential, and you remember that the first order of the Taylor expansion of the exponential function is x without coefficient, then what you get is that you can approximate this potential, and there is an error. These two should not be here. What you get is exactly this. And so what you can see is that this term here corresponds exactly to Ohm's law. But it is an Ohm's law for which the conductance, so sorry, let me put it here. So Ohm's law corresponds to a current that increases the as a potential difference increases. And this is a Ohm law for which the conductance is given by this whole expression. So you see here, you are dividing the leak current by the thermal potential. So see, this has the dimension of a conductance, but it is a conductance that essentially depends on Vg and Vd plus Df. So it's a voltage-dependent conductance, which means that you can easily tune the conductance of this resistor by changing the different potentials. Okay, so first actual circuit using one transistor, and this is a voltage to current logarithmic converter. So this is IV, but actually what we are doing is V to I conversion. And so for this, you use the transistor in the saturation regime. So you use this expression here, and you realize that if you express the this is I to V converter. Sorry. So this is it's correct. So we are doing I to V conversion. So you see that a standard transistor is already a voltage to current converter according to this expression or according to the full law. Now what we want to do is to use a transistor as a converter from current to voltage. And if you invert this expression here for the saturation regime under the condition that you are keeping the drain at the same voltage as the gate, so you literally draw a cable that goes from the gate, or you take the gate terminal and you connect it with an electrical cable to the drain of the transistor, then essentially you are controlling the gate here from, so now you have a way to move charge from the gate to the drain, and so now you have a way to use the current to the transistor to translate it to voltage, and in particular to the gate voltage. And but okay, in general, you can either invert with respect to the source or with respect to the gate. This is the configuration or the expression that we will mostly use. So controlling the current to the transistor to control its gate source, which is also the voltage of the drain. Okay, and the two transistor circuit that is very important for neuromorphic engineering is what's called the current mirror, for which you again use transistors in saturation regime. So when this is the ruling law, and essentially the principles of a current mirror is that you are using the first transistor as a current to voltage converter, and then you use this voltage here to generate current in the second transistor. And so if you do the computation, they're easy. What you get is that if the two transistors are perfectly identical, then the current in the second transistor will be a copy of the current in the first transistor scaled by this exponential coefficient that depends on the source voltages and not on the drain voltages, because you are keeping them in saturation. So this is when the two transistors are equal, if your two transistors have different dimensions, and in particular, if you call M the ratio W2, so width of second divided by length of second, all divided by width of first divided by length of first transistor, then you can have an extra gain in front of your that defines the current that you will be measuring at the output of the transistor. And so, for instance, we use these in the chip we produced because we wanted to, so as long as everything remains inside the chips, you can use very low current, very low voltages because the noise level inside the chip per se is not high, charges are traveling not far, and so on and so forth. But now if you really want to measure something from your chip, you need signals that you can measure with an oscilloscope, essentially. And so what Larice did was to take the current that represents the membrane voltage for his neuromorphic neurons and plug it into a current mirror where M was 500 in such a way that he managed to transform tenths of nanoampere into essentially microampere, which is still small, but microampere are definitely measurable off chip. But there are many, they have many other applications, and we will see a few of them in a second. Another simple circuit that uses only three transistors is what's called the differential pair. So again, you have all transistors are in saturation for the differential pairs, which means that you have to put a sufficiently high potential here at the drain in such a way that the voltage drop from here to here is larger than 800 millivolt. Yeah. Did I hear something? No. In such a way also so that you have 800 millivolt from here to here and 800 millivolt from here to ground, or to the rest of the circuit you put here. And so for this, this potential should be sufficiently high. If this is the case, then let's see what's going on. So you have that the current that's flowing here is fixed by this potential here. So because you're in saturation, what's flowing here is mostly controlled by VB, because so this point here is the source of this two transistor, but it is the drain of this transistor here. And so if you are in saturation, the current does not depend on the drain voltage. And so the total current that flows here is fixed by VB, which means that the sum of I1 plus I2, so you see that you have a current that flows here, a current that flows here, and these two adds up at this node and flow through to this transistor, which means that the sum of, it's written here, the sum of I1 plus I2 is exactly IB, which is given by this expression. And then you also have that I1 is given, must satisfy the saturation equation for this transistor, and I2 must satisfy the saturation transition for this equation. So if you solve this equation for I1 and I2, in particular, you can express I0 as a function of IB and plug it here. What you get, you can express I0 as a function of, let me write it down. So this expression here also means that E to the kappa, no, sorry. This means that I0 E to the kappa VB is equal to I1 plus I2. And so now you can replace this I0 here by this term, and you get this expression here if you do the algebra. And look at the expression that we have got. That is, these are exactly sigmoidal Boltzmann equation. And in particular, this tells you that the current through I1 is given by IB times this expression that probably is more easy to read if you factor the exponential of V1 at the numerator and denominator, and you get this expression here. And so you see that I1 is a sigmoidal Boltzmann function that is monotone increasing with V1 and monotonically decreasing with V2. And that's exactly half IB when V1 is equal to V2. And the mirror symmetry for I2. So instead of having V2 minus V1 here, you have V1 minus V2. You can use differential pairs for various things. One thing that you could use it for are what are called transconductance amplifier. And in particular, what you want is an object that has the characteristic of so something that at the so that if you define this node here as the output of your circuit, I out will be 0 when you have zero voltage difference at the two terminal controlling terminal of the amplifier, and for which the current increases when you increase the difference with V1 minus V2 and decreases when you decrease this difference or you make it negative. And so you see that so I1 and I2, although you have V1 equal V2, you will have that I1 is equal to I2, and both of them will be equal to IB over 2. But so if you take this current as output, you don't have something whose output is 0 when the differential input is 0. But if you manage to have the difference between I1 minus I2 as output, then this will do the trick. And so a way of doing it is to use Kirchhoff's law in the following way. So you can use a current mirror here. So this is we saw a FET current mirror, but this is actually a this block here is a FET. Sorry, Tony. Is a FET current mirror. And so this means that you will have a copy of I1 will be here. So thanks to this current mirror, you have I1 that's copied here. And so if you apply Kirchhoff current law, you have that I out is equal to I1, because I1 is entering this node, I out is going out, and 2 is going out from the node minus I2. But essentially, the full Kirchhoff, the actual Kirchhoff law, it tells you that the net current at the node must be 0 because charge is conserved. And so you have the 0 is equal to the current that enters the node, so I1, minus the sum of the current that goes out from the node. And from this, you get that I1, that I out is equal to I1 minus I2. Okay, so now if you put everything together, so if you use the expression derived in the previous slides, and you remember the expression for the hyperbolic tangent, which is basically a function that has the difference of an exponential at the numerator and divided by the sum of the exponential at the numerator. Putting everything together, you get that I2 minus I1 exactly has the formula of an amplifier. So in particular, that this output current now will be 0 when V1 minus V2 is 0, and will increase like an hyperbolic tangent when this difference is positive, and decrease negative when this, again, as an hyperbolic tangent when this difference is negative. moving on in complexity in terms of circuit, we can use the transconductor amplifier as an amplifier. And once you have an amplifier, you can use feedback from the output of the amplifier. Well, it's in the next slide. So we can use negative feedback, which means you take the output and you feed it back. So you draw a wire from the output terminal to either of the two input terminal. If you put this wire from the output to negative, this will work as a negative feedback amplifier. If you put it from the output terminal to the positive terminal of the amplifier, this works as a positive feedback amplifier. And the unity gain follower works in negative feedback configuration. And so now the output voltage will be defined implicitly by these, not implicitly, will be defined by this expression. And now if you keep I out constant and you use implicit differentiation to compute the gain from V1 to V out, you have that this gain will be equal to A divided by A plus 1, where A is computed not in a very easy way, but is essentially the output impedance of the is a measure of output impedance of the amplifier, and this will be equal to the early potential, which we didn't see and we will not see because it's a slightly more advanced topic. So this is the early potential, which, depending on if you use sufficiently long transistor, is probably around maybe 10 millivolt. And so you have something that's, so if you look at this number, you have 10 divided by, no, sorry, no, early potential is super large. Sorry. This will be around, I don't remember, but few tenths of volt. Tenths of volts. And so you have a number that's, let's say, 50 or 100 divided by 0.8 plus divided times a number that's order 1. And so A is a very large number, which means that this number here is more or less 1, which means that if you use this configuration, then V out follows V1 in a way that completely isolates these two terminals. And so you have a way to use V1 as a driver of another circuit without charges that are drained to RV1, and so in a way that allows you to build things that are modular. One easy thing you can do is to put a capacitor at the output voltage, and as long as you remain in the linear region, in the ohmic region of the transistor, you can linearize the hyperbolic tangent. And so now if you write the current, the Kirchhoff law here, considering that there is no current that goes in this direction, so no current here because the input impedance is very high. And essentially you are injecting, you are connecting at the gate of a transistor, and so there is nothing that can flow inside there. Then Kirchhoff's current law simply tells you that the capacitive current, which is simply CV out dot, is equal to A out. And now you can replace the expression we just derived, linearize the hyperbolic tangent, and arrive at this equation for the output voltage. So you see that you already, with just a few transistors, we already built a circuit that can realize first order ordinary differential equation. And so, as you can imagine, this is a very fundamental, you can imagine. As you know, thanks to what Omar is teaching you and surely other courses, you already have one of the most important building blocks of neural dynamics, that is essentially the dynamics of the membrane potential. You can control the time constant of this first order linear differential equation through this parameter. And in particular, you can use IB, which can be fixed by the bias voltage of the transistor of the transconductance amplifier you have here. And by changing this current, you can make your first order dynamics more or less fast, more or less slow. I think I will end here because the differential pair integrator is slightly tougher to understand, and I would like to at least give you an idea of what's going on. And same for the Hured-Muth circuit. So I think I will start next lecture from here, because this DPI and this other circuit, which implements another form of sigmoidal nonlinearity, are really at the basis of the neuromorphic neurons we designed in our lab. And so I think it makes sense to start again from there. And then I think that the next team are, it's Loris neuron. So I think it makes sense to stop here. Do you have any questions? Okay, in this case, I hope you enjoyed the lecture, and we can say goodbye.
Well, thank you very much, Dr. Alicia. So then that concludes our first part. Well, the first part of this crash course to neuromorphic engineering. So thank you very much. If you could share with us the slides and the pending exercise about, you mentioned one exercise, right?
I mentioned one extra slide.
Yeah. Well, anyway, if you could share with us.
I will share you a keynote presentation.
Okay.
And maybe I will convert it to PowerPoint as well. And then the PDF of the more mathematical part. And
Okay.
and then I think I would share you a folder actually, and in this folder I will also be dumping papers and material that is collateral to this to what we're looking at.
Okay. Thank you very much then. Well, thanks all for being here, and see you all next Monday, please.
Bye bye. Have a nice
Thank you,
day.
doctor.